Alrighty guys, we are back. Today we are going to be using the skills we learned from last lesson, solving log equations, and we will be using them to help us solve exponential equations. So we've actually been doing this a whole bunch already, except we were solving the equations graphically. So for example, question like this. Like, when is she going to have $100,000 in her account, right? We were solving this graphically before, but now we will be able to solve a question like this using logs. So this is really more or less actually, I think it's kind of like a review lesson, right? Because we already know how to solve log equations. We're just applying it to some older style problems, some older style exponential problems, all right? So why don't you guys try this warm-up, and also want to remind you we're going to have a test on Monday, right? Topics have already been posted. So go ahead, pause the video, and try this warm-up. All right, so if a population doubles every 5 years, how many years will it take for the population to increase to 10 times its original amount? All right, so we haven't done this in a while. But we can write the final population is going to equal the initial population times our growth factor, right? In this case, it's 100% growth because we're doubling. So that's 1 plus 1, or 2. All right, so we're doubling, right? And if it were every year, I could just write to the t power, right? But it doesn't double every year, it doubles every 5 years. So I really shouldn't even say my growth factor is times 2 because it's not doubling every year, it's doubling every 5 years. So what could I do to get the actual growth factor, or how should I change the exponent? All right, so initial population here, it doubles every 5 years, so 1, 2, 3, 4, 5, right? We haven't done this in a while, so I'm just going way back. All right, so in 5 years, we multiply by 2. So how much are we multiplying by each year? Well, we're really going to multiply by the 5th root of 2, right? Because we multiply by the 5th root of 2 5 times, that is equal to 2. So we're multiplying by 2 to the 1/5 power. In other words, each year. So that is our true growth factor, 2 to the 1/5 power, which is also why we can just write this as 2 to the t over 5 power. Right? Because we could write this as 2 to the 1/5, all raised to the t power, which is t over 5. Right? So there is our formula. We want to know how long it takes for the population to increase by a factor of 10. So it doesn't matter what the initial and final population is. If this initial population were 1, this will equal 10. Right? If it were 2, it would equal 20. But however you do it, once you simplify, there is your equation. Your final population will be 10 times. And there we go. And I don't even know why I'm doing this. The question just asked, without a calculator, narrow down your answer to a 5-year interval. So let's say in 5 years, we're going to double. It's going to be times 2. In 10 years, it's going to be times 4, right? 15 years, we're going to double again, times 8. And in 20 years, we're going to have times 16. So I know my actual answer should be somewhere in between 8 and 16. Not 8 and 16, sorry. It's going to be somewhere in between 15 and 20 years, right? Because times 10 is somewhere over there. So if I had to guess, I would say like 16-ish years. All right, so there's the equation we found earlier. So to solve this log equation and get to the nearest 10th of a year, well, using our log rules, to solve this equation, we can take the log of both sides. So log of 10 equals log of 2 to the t over 5, right? So using log rules, I can bring that t over 5 to the front. And I get log 10 equals t over 5 times log of 2. And now I can divide both sides by log of 2. Right? And I'm just using the common log here. That's log base 10. Right? And if you want to be weird, you can choose a different base. You can take the log base 2 of both sides. But why would you do that? Because it's more work. So just take the common log, right? Or log base 10 of both sides, which we just write as log. So anyway, I'm going to divide both sides by log of 2. That cancels. And I can also multiply both sides by 5, right? Times 5. That cancels. And times 5 on this side. So this is what I would type into the calculator. 5 times log of 10 divided by log of 2. And typing that in, we're going to get t is about 16.6 years. Right, and that is definitely in line with our previous guess, right, or estimation, between 15 and 20 years, 16.6 years. All right, so number 1 down here, to the nearest hundredth solve by writing in logarithmic form. So this first one, I can divide both sides by 17. 5 to the x over 3 power equals 4 over 17. And you can take the log of both sides here, or you can write this in log form. So you have a couple options. I just want to show you that you have a couple options. But I do say by writing this in log form. So normally what's easier is to just take the log of both sides. So if I take the log of the left side and I bring that exponent to the front, that's x over 3 log of 5 equals log of 4 over 17. Right, and then I can just solve for x here by dividing by log of 5 and multiplying by 3. Really similar to the warm-up. Right, but another way to solve a problem like this is to write it in logarithmic form. So we know if we have log base b of a is equal to y, right, in exponential form, that's b to the y is equal to a. So we want to start with exponential form, right, and go to logarithmic form here. So our base here is 5. So I know it's log base 5 of 4 over 17 is equal to the power, x over 3. So doing it this way, you can also write it in log form and then just multiply both sides by 3. Get 3 times log base 5 of 4 over 17 is equal to x. And just type that into your calculator, get that to the nearest hundredth, and there we go. That's solving it by writing it in log form. We could have done that as well over here. We could have written this in log form and just solved it that way. But another method for solving these kinds of exponential equations is to just take the log of both sides, right? For this next one, we need to do a little simplification first before we can solve, just like this one, right? This one, let's add 3 to both sides. We get 4 times 2 to the x is equal to 20. Divide both sides by 4. Right, we get 2 to the x is equal to 5. And now we can write that in log form, or we can also take the log of both sides to solve. Right, so it's really up to you. Just make sure you can do it both ways. But writing this in log form, that's going to be log base 2 of 5 is equal to x. And just type that into your calculator, round to the nearest hundredth. Right? All right, now for some word problems. A hot liquid is cooling in a room whose temperature is constant. So let's say we had coffee and it was just sitting in a room. Its temperature can be modeled using the exponential function shown below. Its temperature T is in degrees Fahrenheit, and it is a function of the number of minutes M it has been cooling. So do you guys remember the coffee problem from a long time ago, way before remote learning started? We had to figure out what temperature Mr. Chug liked his coffee at, right? And we modeled it with a square root function, a negative square root function. Well, I'm sorry to tell you, but that was all a lie, because square root functions don't model cooling. Equations like this model cooling. So the initial temperature of the water at time 0, or I guess it's water that's cooling in this case. So we just plug in A0 for M, and we're going to get the initial temperature to be 101 times e to the, well, 0 times negative 0.03 is 0 plus 67. So e to the 0 is 1. Our initial temperature is 101 plus 67, or 168. So 168 degrees Fahrenheit. How would you interpret the statement T of 60 equals 83.7? So apparently if you plug in 60, you're going to get 83.7. So let's take a look at what the input is. As a function of the number of minutes M it has been cooling. So I'm plugging in a 60 for M. So after 60 minutes or 1 hour, the temperature is going to be 83.7 degrees. Right? After 60 minutes, the temperature of the water has cooled to that number. All right. So what is the decay factor? What is the rate of decay each minute? Well, this is actually like or compounding continuously, but a little different, right? Hopefully you guys remember the PERT formula, right, where the R is the rate of growth. Right, so in this case, it's just like a PERT formula, but it is shifted up 67 units. Right, so this negative 0.03, that's actually the rate, right? The R in this example is negative 0.03. So I haven't talked about this, I probably should have talked about this earlier, right? But we know in the PERT formula, we just plug in for the R. So if the R is negative, well, that indicates a decrease or a rate of decay. And of course, when the R is positive, that's a rate of increase. So the rate of decay is just change this to a percentage. It's 3%. So it's 3% decay each minute. In other words, the water cools by 3% each minute. Right? What will the temperature approach as M approaches infinity? What do you think this value represents? So if I plug in a really, really, really big number for M, right? Let's say, let's not make it too big, but let's just make it like 100, for example. But what's going to happen? We're going to get this equal to 101 times e to the negative 0.3 or negative 0.03 times 100 plus 67. So what's going to happen here is we're going to get a big negative exponent, right? Imagine if I plug in a bigger number, like 1,000 or 1,000,000. I'm going to get a very, 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 very big negative exponent. So let's say a big negative number. I'm just going to make it a big number, right? I'm not plugging in 100 anymore, just a very big number. And so what is e to the negative very big number going to equal? Well, that's going to be 1 over e to a very, 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 very big number, which is really close to 0, right? It's going to be minuscule. So it doesn't matter that that's a 101. Eventually, this is going to approach 0, right, as m gets very big. And so what I'm left with is just 67. The temperature is going to approach 67 degrees as m gets very large. Right? So let me erase that for a sec. Let that sit with you for a second if that doesn't make sense. But as m gets very large, right, that approaches 0. 0 times 101 is 0. And so we're going to be left with 67. Right, so as m approaches infinity, the temperature as a function of m, which is the number of minutes. So as this thing sits outside, for infinite number of time, it's going to be 67 degrees. So what do you think this 67 degrees is? Well, that is going to be the ambient or surrounding temperature of our water, right? Because if you just leave water out for a long time, it's going to cool down to not 0, it's going to cool down to room temperature. So that's the ambient, or I can say room temperature. So using the natural logarithm, determine algebraically when the temperature of the liquid will reach 100 degrees Fahrenheit. Show the steps in your solution, round to the nearest tenth of a minute. So let me copy my equation again. Well, yeah, let me just write it down. So 100 is going to equal, forget the numbers, 101 e to the negative 0.03 m plus 67. So I set the temperature equal to 100, and all we got to do now is solve this equation, right? So to solve this equation, you want to isolate this exponential expression I'm highlighting right there with the base, right? You don't want any coefficient, you don't want anything added or subtracted with it. So we're trying to isolate for this. Then we can take the log of both sides, or we can change it into logarithmic form to solve this equation. So subtracting 67 from both sides, I get 33 equals 101 e to the negative 0.03 m. Divide both sides by 101. I get 33 over 101 equals e to the negative 0.03 m. Right? So personally, both methods are pretty simple to solve from here. You can take the log of both sides, or, as I said before, you can write this in logarithmic form. But because our base is e in this case, you can take the log of both sides. You can take log base 7, log base 2 of both sides if you want. But because this is e, I think it makes most sense to take the natural log of both sides if you're going that route. Or if you're changing it into logarithmic form, just go with the natural log, makes it easier. So I think I would change this to, I'll do it both ways, just this example. And then I think from after this example, I will just be taking the log of both sides, because that is the method I prefer. But we'll do it both ways, just for this first one. All right, so changing to logarithmic form, our base is e. So it's log base e, which is the natural log, right, of, well, I know it's equal to my exponent, because it's a what power function. So it's equal to negative 0.03 m. And it's going to be the natural log of 33 over 101. So from here, I can divide both sides by negative 0.03, divide this by negative 0.03, and type that into your calculator, and you should get the value of m. Right, and let me do it the other method, which will be taking the natural log of both sides. So I take the natural log of 33 over 101, set that equal to the natural log of e to the negative 0.03 m. You can take this, bring that to the front. So natural log of 33 over 101 equals negative 0.03 m times the natural log of e. But what is the natural log of e equal to? Right, ln of e is equal to 1. Right, because again, this is saying e to the what power, right? Natural log is just log base e. E to the what power equals e. E to the first power equals e. Natural log of e is 1. So you see we're getting the same exact setup, and just type that into your calculator. And I actually just got TI Inspire app registered on my calculator, so I can now show you that. I'll just do this calculation. Let's see if this works. Let me switch the screen I'm sharing to TI Inspire. Right, so hopefully you guys can see this. So if you want to do the natural log, where's the natural log button? It's really small font. Control, it's right there. ln of 33 divided by 101 And we're going to take all of that and divide it by negative 0.03. There's my negative. And you hit enter. So that is 37.2871. 37. And what was the rounding? To the nearest tenth of the minute. So 37.3-ish minutes approximately. All right, and let me switch back now. All right, hopefully that showed up. I'm going to check in the video after to see if that worked. But you didn't miss too much. If it didn't, just type that in your calculator, 37.3. Let's see if that makes sense. So we know after 60 minutes, the temperature is 83.7. So looks like it checks out, right? And of course, if you want to really double check, just type that equation into your calculator, graph y equals 100, right? And see where they intersect. So now we don't have to do it that way. We can do it algebraically by taking the log of both sides or changing it to logarithmic form. Right, so next problem. A biologist is modeling the population of bats on a tropical island. When he first starts observing them, there are 104 bats. The biologist believes the bat population is growing at a rate of 3% per year. Right, an equation for the number of bats b of t as a function of the number of years t since the biologist started observing them. So the number of bats is going to equal the initial number of bats, which was 104 when you started observing them, times, right, 1 plus or minus our rate of growth or decay. In this case, it's a rate of growth, so it's going to be plus the rate of growth, 0.03, and it's just 3% per year, so it's just to the t power. And using our equation from part A, algebraically determine the number of years it will take for the bat population to reach 200, round to the nearest year. So we're solving this equation, 1.03 to the t power. And hopefully you see this is not too bad, right? Divide both sides by 104. 200 over 104 equals 1.03 to the t power, right? Change this to logarithmic form or take the log of both sides, and you can solve for t. All right, I'm not even gonna get that answer for you. I'm sure you guys can do that. And yeah, I will do the last two. Those are a little more interesting. All right, so number 4, Hannah invests in a savings account that compounds monthly at a nominal rate of 3.2%. If she invests $3,000, approximately how many years will it take for her account to accrue $10,000 in interest round to the nearest year? All right, so here's our compounding monthly stuff, and we're combining it with solving it as a log equation. So I'm going to write the compounding monthly formula, or just the compounding formula in general. So I think I used A before. Right? It doesn't really matter what letters you use, but your final amount is going to equal your initial principal, the amount you put in, right, times 1 plus your rate over your compounding frequency, which in this case will be 12, to the n-t power. All right, so if you guys forgot compounding by some time period, there it is. So she invests $3,000. 1 plus the rate is 3.2%, so that's 0.032 over 12 to the 12t, and we're solving for t. So you gotta be a little careful. We want for her account to accrue $10,000 in interest. So her final amount is not going to be $10,000. It's going to be $13,000, right? 3,000 plus the $10,000 in interest that she wants. So solving this equation, same as before. Divide both sides by 3,000. This will equal 1 plus 0.032 over 12 to the 12t power. All right, we could change this to log form, but I think personally it's easier just to take the log of both sides. There's really less thinking. right? Once you know your log rules, we can just simplify using log rules. So just gonna write in the same step. Take the log of that, take the log of this, right? Take the log of all of this. Using the log rules, we can bring the 12t in front, write that as a coefficient, right? So that becomes that. And I'm solving for t, so I'm going to divide both sides by that crazy log. So 12t is going to equal this divided by all of this. Right, and this one I will show you typing it into the calculator just in case. Right, it's a lot to type in. And then finally divide both sides by 12, right, to get t by itself. You might want to do that in 2 steps, but I feel comfortable multiplying by 1/12 on both sides and just sticking the 12 down here as part of that denominator. So hopefully when I type all this into my calculator correctly, I will get an answer that makes sense. So let me switch screens again to calculator. And let's type in. Well, first I got a fraction, so control divide. Here's my log button. I don't need to type in the base because I know it's the common log. But that's going to be 13,000 over 3,000 divided by 12. Control log of 1 plus 0.032 divided by 12. I hit enter, and it's going to take approximately how many years? Round to the nearest year. It's going to take about 46 years for this to happen. All right, t is about 45.8841, or around 46 years. And I think that makes sense to me. That sounds reasonable. It wasn't like in 2 years or something crazy like a million years. So it's kind of hard to estimate, but I think this answer makes sense to me. So assuming I didn't type anything in incorrectly, there is our answer, 46 years. All right, and finally, oh, hold on, am I sharing? All right. Carbon-14 has a half-life. Oh man, half-life. So you see, we can really bring back any of those exponential topics that we've been working on before. Compound interest, just basic exponential growth, the percent manipulation stuff, right, which I know you all enjoyed. Right, that's all fair game with logarithms because now we can solve those equations using what we learned recently. So half-life. All right, carbon-14 has a half-life of 5,730 years. You're presented with a document which purports to contain the recollections of a Mycenaean soldier during the Trojan War. The city of Troy was finally destroyed in 1250 BC, or about 3,250 years ago. Carbon dating evaluates the ratio of radioactive carbon-14 to stable carbon-12. All right, by the way, I did not make up this question, if you can't tell. I got this from, I think, Purple Math. So given the amount of carbon-12 contained from a measured sample cut from the document, there would have been about that many grams of carbon-14 in the sample when the parchment was new. Assuming the proposed age is correct, according to your equipment, there remains that many grams. Is there a possibility that this is a genuine document, or is this instead a recent forgery? Justify your conclusions. So pretty much we want to check if the age of this actual parchment is that many years old. So we're going to use the numbers they're giving us to get the age of it based on the carbon numbers, and let's see how well it matches up with the actual age it's supposed to be. So hold on, I have this in my notes somewhere. All right, so half-life. Do you guys remember the half-life formula? Well, If you don't, that's fine because we can rederive it. We don't really need the half-life formula, right? But we have some, let's say we have some final amount, I'll fill in the numbers later. That's going to equal some original amount. So the half-life is how long it takes for half of whatever you have to decay, right? Half your initial amount to decay. So here's my initial amount times a half. So if it takes 5,730 years for it to decay in half, well, if it decayed every year, it would just be 1/2 to the t power, right? But if we do this step thing again, right, it takes 5,730 steps. So there's going to be a lot of steps here for it to go by times a half. So what are we multiplying by each step? Well, we're really multiplying by a half to the 1/5,730th power, right? Which was how long it takes for it to get multiplied by half overall. So I can just make this exponent t/5,730. All right, so that's the way to think about it in case you forgot the half-life formula. But if you want the half-life formula, here it is, A of t equals the initial amount times 1/2 to the t/h, right? Pretty simple. You don't need to memorize that because I just figured it out like this. All right, so there would have been 1.3 times 10 to the negative 12 grams of carbon when the sample was new. So that's going to be the initial amount of carbon in this parchment. 1.3 times 10 to the negative 12. Put that in parentheses. T5730. And according to your equipment, there remains that many grams. So that's the amount of grams that remain today. 1.0 times 10 to the negative 12. And really now it's just like all the other problems we've done, except the numbers are kind of weird and messy. But I would divide both sides by that quantity. And in fact, I can cancel out the times 10 to the negative 12. That's going to cancel out on both sides. So we get 1.0 over 1.3 equals 1/2 to the t/5730. Right, I'm going to take the log of both sides. The log of 1/1.3 equals t/5730. I'm bringing the exponent to the front preemptively. Equals that. Divide both sides by log of 1/2 and multiply both sides by 5730. So t is going to be 5730 times the log of 1/1.3 divided by log of 1/2. All right, and I don't know if you guys want to see me type this in again, so I am not going to type it in again. I'll just tell you the answer. All right, the answer is, why does it keep pausing my share? T is going to be approximately 2168.87 something something something. They'll tell us what to round to. No, but based on the actual carbon amounts, right? The document is 2,169-ish years old, which is about 1,000 years off from what it would actually be if it came from the city of Troy. So is this a recent forgery? So while it might not be a recent forgery, it is definitely not from the time period, right? It's about 1,000 years off. So probably not a genuine, I would say, article from the time period or something like that. It's a weird question at the end, but there's the math to support it. And that's going to be it for solving exponential equations using logarithms. All right, hopefully you got some good review for stuff like compound interest, half-life, right? Percent manipulations, we didn't really do too much of that, but make sure you still can do that. And that's going to be it for today. Any questions, as always, let me know. Test is going to be on Monday. All right, hope you guys are taking care of each other. I hope your families are good. And take care, guys. See you guys later.